Hey guys, it's 1212, chapter 21, nuclear chemistry, part 3. I'm picking up, following the PowerPoint on, I left off last time on slide 15. That's where we introduce the math side of nuclear chemistry, where we do calculations based on half-life. So the half-life of a sample is essentially this amount of time that it takes for half the sample to react and turn into something else. This process, the half-life is a constant value for first-order reactions, and we've said multiple times that natural nuclear decay or radioactive decay reactions follow first-order kinetics. So when we solve these problems, we're going to use our first-order equations that we learned previously. AT equals A0 times e to the negative KT is one equation. We rearrange that or integrate it, we get the ln of AT over A0 equals negative KT. And then one more equation that is important. If they give us the half-life, sometimes they'll give us that value but not give you the K value. So we have a little equation, the half-life, which is labeled T1 half, equals 0.693 over K. All right? With those three equations, we should be able to solve all the basic problems that we do that involve half-life and radioactive decay. All right? So, on slide 15, again, most of this section is going to be problems, so that's why I'm just going to work on the chalkboard. But on slide 15, it introduces what half-life is. It has a table that has a lot of different isotopes of different elements and just shows the variations that you can have in half-life. Some half-lives of some elements will be on the order of a few minutes or hours. There are other ones where the half-life might take years. And I think uranium-238, the half-life is actually like 4.5 billion years. Okay? So, the amount of time is proportional to how stable the nucleus is. But an important thing there is it doesn't matter what chemical form the atom is in. Okay? So, carbon-14 is radioactive. The half-life is 5,730 years. It doesn't matter whether that carbon-14 is in the form of elemental carbon, like diamond or graphite, or it could be in the form of CO2 gas or glucose or any other molecule. The form doesn't matter, and in any mixture of or any compound that has carbon, it's going to have some carbon-12, some carbon-13, and a certain percentage of it will be carbon-14. Those atoms, regardless of their form, will always have a half-life of 5,730 years. There's nothing we can do to change that. Even if we increase the pressure or change the temperature or whatever else, the half-life of an atom is based on how stable the atom is. Okay? Now, once we're given a half-life, then we can start working some problems. So if we move to slide 16, first it gives an example where it says iodine-131 has a half-life of 8 days. So that's an isotope that's used in medical labs and stuff like that. If they either inject iodine or if you eat an iodine pill, the iodine tends to collect in the thyroid, and they can use the radiation that's emitted to do scans of your thyroid. So it's a very important element that's used for that purpose. If a lab purchases 20 grams of iodine-131, if it just sits on the shelf for 8 days, half the sample will disappear. Now, what happens to it is it actually changes into another element. It doesn't just disappear from existence, but when iodine-131, I think it undergoes beta decay, it'll actually turn into, I think the element beside it is krypton. It turns into krypton, which is a gas, which the iodine's a solid, krypton's a gas, so when it converts, it does turn into the gas and float away. So in that case, the sample does disappear from the solid, but there are other times where it changes from one solid element into another solid element. So we're losing the element we started with, but it's just converting into something else. Okay? It doesn't truly disappear. So that sample, if we have 20 grams, after 8 days, we will only have half of it remaining, so that would be 10 grams. If you wait 8 more days, then you'll be down to half of that, which would be 5 grams. And then after 8 more days, you cut it in half again, and you'd be down to 2.5 grams. So every 8 days, you're going to cut the amount of sample in half. And it's a gradual process. It's an exponential decay, which if you look at the graph on slide 16, it shows the amount of the iodine sample every 8 days is cutting in half, and it gives you an exponential decay. All right? So that's just an example of kind of how the math works. The equations that we need are here. So then we look at the next problem. At the bottom of that slide, it says the isotope of iodine is iodine 123. It's a different isotope, so it has a different half-life from the one above it. The half-life of this one is 13 hours. And it asks how much of a 64 milligram sample will remain if we wait 26 hours. Now, I could solve it with one of these equations and do some heavy math with it, but I also can apply a little bit of logic and say, okay, if it's 26 hours that have passed, they told me that the half-life is 13 hours. This is twice the half-life. After one half-life, I would cut the amount of sample in half. After the second half-life, I'll cut it in half again. So the amount of sample is going to be 64 milligrams divided by 2, and then divided by 2 again. So after 26 hours, I'm going to have 16 milligrams remaining. Okay? Now, that's just, I kind of did that in my head because the numbers are pretty straightforward. I know that the time, if it's a multiple of the half-life, then you can apply that logic. Okay? It kind of creates another equation that's not like these. It's a little bit more simple. I could say that AT, the amount of sample that remains, is going to equal A0 divided by 2 to the n. The n stands for the number of half-lives. So if I start out with 64 milligrams, that's A0. I can divide by 2 raised 26 hours is 2 half-lives, so n equals 2. I can plug that in right here. 64 divided by 2 to the second, which will give me 16 milligrams. That's the math that we could do. Okay? So when the half-life is a multiple of, when the amount of time that's passed is a multiple of the half-life, then we can use this equation and do more simple math. If it's a little harder, then we're going to have to use the equation up above. Okay, so let's work the same problem using the other equation and just see if we get the same answer. So I'm going to use the top equation. AT is the amount that's remaining. That's what I'm solving for. Equals A0 is 64 milligrams times e to the negative. Now, a problem I have, they didn't give me the value of k. They did give me the half-life, though, so I can use this equation to find the half-life is 13 hours equals 0.693 over k. I can solve for k. So I multiply k over, divide by the half-life. So in this case, k is going to equal 0.693 over 13. And the units will be hours to the minus 1. So if I divide that, I'll go ahead and do that real quickly. 0.693 divided by 13. The value of k is going to be 0.0533. Hours to the minus 1. Times the amount of time that has passed is 26 hours. So now, if you work that out, we should get AT equal to 16 milligrams. Okay, so I would say that's a more rigorous method. This equation and the setup we just did, that will always work for any problem involving half-life in a radioactive decay. Our way that we did it a few minutes ago only works if the time is a multiple of the half-life. It's kind of a shortcut. It's easier math, but it's only going to work sometimes. Okay? So now let's move to the next problem. So the problem reads, the half-life of zinc 71 is 2.4 minutes. If we had 100 grams of the sample at the beginning, how many grams will be left after 7.2 minutes have elapsed. So, first question, can I use the shortcut, or do I need to use the full equation and the math up here? Okay? Well, to figure that out, I'm going to take the total time, divide it by the half-life, and just see if I get a whole number. 7.2 minutes divided by 2.4 minutes is the total time divided by the half-life. That does come out to be 3. So what that means is 7.2 is 3 times the half-life. So I could use my simple equation, AT equals A0 over 2 to the n, and the n value is going to be 3. All right? So I'm going to plug my numbers in. AT equals 100 grams over 2 to the third. And if you divide that out, 100 divided by 8, it's going to be 12.5 grams. So that's the answer to that problem. You could also plug into this equation, use the half-life to find K, and then solve it that way. You should get the same answer either way. You just have to decide which equations you're going to memorize. Keep in mind, none of these equations are going to be provided to you on the test. First order equations, you have to memorize them. All right, next question. After 24 days, 2 milligrams remain of a sample that originally weighed 128 milligrams. What's the half-life? Okay, so essentially on this one, I can do, again, if I think about it, 128, if I divide by 2, I get 64. Divide by 2 gets to 32, 16, 8, 4, 2. So to go from 128 milligrams down to 2 milligrams, I can get there by dividing by 2 over and over again. So that tells me that the amount of time that's passed is a multiple of the half-life. So I'm going to use my simplified equation. AT equals A0 over 2 to the n. I'm going to plug in the numbers. A0 is 128. AT is 2. So 2 equals 128 over 2 to the n. If I rearrange that and bring this up, bring the 2 down, 2 to the n is going to equal 128 over 2 is 64. And I believe n equals 6 in that case. Again, how many times do you multiply 2 times 2 times 2 times 2 to get 64? I believe that is 6. So n equals 6. That means that the amount of time that has passed is 6 half-lives. Well, they told me 24 days is the total amount of time. That's 6 times the half-life. So if I divide the 6 over, the half-life is 4 days. Okay? Again, that's me kind of using logic and figuring my way around it. You could also have just plugged in up here 2 milligrams for AT, 128 milligrams for A0. The total time is 24 days. If you set all that up and solve for K, then you can plug in the K in this equation, 0.693 over K equals the half-life. That's an alternative way to solve the problem. You should get the same answer once again. All right, next problem. I have 10 grams of tungsten. The half-life is 23.9 hours. I have 10 grams of sample. So how much will I have left at the end of one day? Well, there's 2 ways to solve this problem. One is I can estimate it and get a pretty close answer. or I can plug everything in and get the proper answer. Okay? If I want to estimate it, I would say 1 day is pretty close to the half-life. So I know the answer should be around 5 grams. After 1 half-life, the amount of sample should cut in half. So the answer is going to be around 5. It actually should be a little bit less than 5. Because if 1 day has passed, which is 24 hours, that's a little bit more than the half-life. So at 23.9, I'll be at 5 grams. If I wait a little longer, I'll be under 5. So I know the answer, A sub t, is going to be a little bit less than 5 grams. Okay? That's an estimated value. If it's a multiple choice question, I might be able to pick the answer based on that. Okay? If I want the actual answer, then I'm going to have to plug it in. And now this is the first time we've done one. 24 hours is a day is not quite the same as 23.9, and it's not a multiple either. So in this case, I really need to use the true equation up here and find AT equals A0. Actually, I'll just plug in the numbers. A0 is 10 grams times E to the negative. Again, K is not given. I have to do 0.693 over 23.9. So that gives me 0.0290. 0.0290 hours to the minus 1 times the time is 23.9. So now I can solve that for AT. Oh wait, no. Actually, I need to put in 24 as my time there. I messed up. 24 hours is the time that has passed. 23.9 was the half-life. So, I got 4.98 grams of tungsten is how much remains. Okay? Let's see. So next slide talks about the carbon cycle, where radioactive carbon is actually produced in the upper atmosphere. Again, the slide tells you a little bit about that. You can read about it if you want to. But carbon-14 is used for dating organic materials. Any living organism, while it's alive, it participates in the carbon cycle. So while I'm alive, I'm eating and drinking and breathing in air with CO2 in it and all that. So the amount of carbon-14 in my body is constantly being replenished. While I'm alive, I'm going to maintain a fairly constant level of carbon-14. Okay? But once I die and I get buried, at that point, the carbon-14 in my body kind of gets locked in, and I'm not going to replenish any, but the carbon-14 is going to start to decay, or is going to continue decaying without being replenished. So at that point, the amount of carbon-14 in my body will slowly decrease over time. If a scientist digs out a formerly living material, whether it's an animal or plant, and calculates based on how much carbon-14 is still present, they can back calculate at what time or what year that organism died. This method, the carbon-14 has a half-life of about 5,730 years. So it'll work up to about a original date of 100,000 years ago. And then at that point, if you go past 100,000 years, there's really not enough carbon-14 left to measure. So at that point, your data doesn't work anymore. So carbon-14 dating is effective for organic materials up to about 100,000 years. Okay? So the next problem, it says charcoal from a painting in a cave in France gave a radioactivity count of 2.10 becquerels, which is a unit of radioactivity. Carbon from a tree that recently died gives a radioactivity count of 13.7 becquerels. Okay? Based on that information, calculate the half-life, the half-life is 5,730 years. Calculate how old the charcoal is in the painting. Okay? So, essentially, I'm solving for time. So this time I'm going to use this equation because it's already, like, everything's been moved over, so it'll be easier to solve for time here. Okay? I just like the format of that equation better when I'm solving for time. So I'm going to plug in ln. Now, they didn't give me the amount of carbon-14 in either of the two samples. Okay? And if they didn't give me the amount, what they gave me instead is the radioactivity measurement, the becquerels, is related to or proportional to the amount of carbon-14 in the sample. Meaning, carbon-14 is decaying, gives off radiation. If there's twice as much carbon-14 in the sample, then I'm going to get twice as much radiation coming out. Okay? So whatever the reading was on the radioactivity meter, which might have been like a Geiger counter or something like that, that number is proportional to the amount. Okay? So the tree that just died gave a reading of 13.7. That's like the original reading for something that it just died. It has the full amount of carbon-14. So I'm going to plug that in for A0. It's going to be the 13.70. The sample that's really old, the charcoal, has less carbon-14 in it. So its reading, 2.1, I'm going to put in top in place of AT, 2.10. Equals negative. Again, K was not given, so I have to do 0.693 over the half-life. I got 1.21 times 10 to the minus 4. And then the time is what I'm solving for. So now I'm going to work that out. And I got 15,500 for my time. So I would say that charcoal is about 15,500 years old. Okay? So that's it for that. Now the rest of the PowerPoint, it'd be better if I put the PowerPoint up, so I'm going to cut this video, do one more